Picture this. It's 1976. NASA just landed 2 robots on Mars, the Viking landers. America is glued to its television sets. Scientists at the Jet Propulsion Laboratory in Pasadena are watching data stream in from another world in real time. The experiment is simple. Scoop up some Martian soil, add nutrients, and see if anything eats them. Something reacted. The room erupted. For one extraordinary afternoon, the scientists genuinely believed they were looking at signs of life on Mars. Then came the second test, and the third, and the answer that ended the party. It was just chemistry. Highly reactive Martian soil doing what chemistry does. No biology, no life. Just rocks pretending. That was 50 years ago. Since then, we've sent orbiters, rovers, landers, and probes to 9 planets, dozens of moons, and hundreds of millions of miles of deep space. We've pointed the most powerful telescopes ever built at thousands of distant star systems. We've developed instruments so sensitive they can detect a molecule in a swimming pool. And the count stands at exactly 0. Not one bacterium, not one fossil, not one signal. Nothing. So the question isn't just where is everyone? The question is deeper and more uncomfortable. What is it about Earth, specifically, that makes life possible here and seemingly nowhere else we've looked? The answer will make you see your home planet completely differently. Let's start with the thing most people get wrong. When scientists talk about the habitable zone, the Goldilocks distance from a star where liquid water can exist, they make it sound almost common. Our sun has one, so do thousands of other stars. The Kepler Space Telescope alone identified more than 2,600 confirmed exoplanets, dozens of them sitting right inside their star's habitable zone. So life should be everywhere, right? Wrong. Because being in the habitable zone is the beginning of the requirements, not the end. And the full checklist is brutal. Earth doesn't just happen to have liquid water. It has a magnetic field generated by a spinning liquid iron core that acts as a planetary force field, deflecting the solar wind that would otherwise strip our atmosphere away in a geological eye blink. Mars had a magnetic field too, roughly 4 billion years ago. Then its core cooled and solidified. The field died. Within a few 100 million years, the atmosphere was gone. The water evaporated or froze. Today, the surface of Mars gets hit with radiation levels that would give you a lethal dose in about a year and a half. Curiosity measured it. The numbers don't lie. Venus is even more instructive. It's almost exactly Earth's size. Same mass, same distance class from the sun. By every basic metric, Venus should be Earth's twin. Instead, its surface sits at 900 degrees Fahrenheit, hot enough to melt lead. Its atmosphere is 96% carbon dioxide, with clouds of sulfuric acid. The atmospheric pressure at its surface is 90 times what you feel standing in New York City. Every lander the Soviet Union sent there, and they sent 14, was crushed or fried within hours. Venus and Earth started the same. One of them got lucky, the other became hell. Here's where it gets really strange. Earth has a moon. That sounds obvious, but the moon isn't just scenery. Without it, Earth would wobble on its axis like a drunk gyroscope, tilting anywhere from nearly 0 to over 85 degrees over millions of years. That kind of instability would swing Earth between a snowball and a furnace in cycles too fast for complex life to ever stabilize. The moon is our gravitational anchor. It keeps our axial tilt at a steady 23.5 degrees. That's what gives us seasons that don't kill us. How did Earth get such an unusually large moon? A Mars-sized body smashed into early Earth 4.5 billion years ago. The debris coalesced into the moon. One accident, one collision. Remove that, and complex life on Earth almost certainly never happens. Then there's plate tectonics. Earth's crust isn't one solid shell. It's a jigsaw of moving plates, constantly recycling carbon dioxide through volcanic activity. This planetary thermostat has kept Earth's temperature within a livable range for billions of years, despite the sun growing roughly 30% brighter since life first appeared. Without tectonics, that feedback loop breaks. The Kepler worlds we found give no indication that plate tectonics is common. In fact, most planetary scientists think it may be extraordinarily rare. When you add all of it up, the magnetic field, the large moon, the plate tectonics, the exact distance from the sun, the right size, the right composition, Earth stops looking like a typical planet that happened to get life. It starts looking like the winner of the most improbable lottery in the history of the universe. But here's the part nobody talks about. Even after all of that, the planet still almost killed itself.
For the first 2 billion years of Earth's history, this planet looked nothing like it does today. The sky was a toxic haze, the oceans reeked of sulfur, and the dominant life form, cyanobacteria, a microscopic single-celled organism, was quietly building something catastrophic. These bacteria invented photosynthesis. They figured out how to harvest sunlight and turn it into energy. And as a byproduct, they released a gas that had barely existed in Earth's atmosphere before: oxygen. We breathe it, we need it. To us, oxygen sounds like a gift. But 2.4 billion years ago, oxygen was a poison. It corrodes metal. It shreds DNA. It was chemically lethal to almost every life form on Earth at the time. As cyanobacteria multiplied and flooded the atmosphere with oxygen, 99% of all life on this planet died. Geologists call it the Great Oxidation Event. Some call it the Oxygen Holocaust. Either way, the scale of the die-off is almost incomprehensible. The single greatest mass extinction in Earth's entire history, caused not by an asteroid, not by a volcano, but by life itself, choking on its own waste. The only reason anything survived is because a tiny subset of organisms developed a freakish mutation, one that allowed them to use that poison as fuel. That mutation is the reason you are breathing right now. And here is why that matters for the search for life everywhere else. Astrobiologists have long assumed that if we detect oxygen in the atmosphere of a distant exoplanet, it means life is probably there. Oxygen as a biosignature, the calling card of biology. NASA's upcoming Habitable Worlds Observatory, planned for the 2040s, is being designed specifically to scan exoplanet atmospheres for exactly that signal: oxygen paired with methane. But Dr. James Casting of Penn State, one of the architects of habitable zone theory, has raised an uncomfortable warning. On most worlds where simple microbial life appears, the photosynthesis pathway likely leads to the same outcome. Oxygen floods the atmosphere, nearly everything dies, and the slim chance of a lucky mutation that rescues the biosphere never comes. The oxygen is real. The life that produced it is dead. What we might actually be detecting across the light years is not a living world. It might be a graveyard with a breathable atmosphere. Oxygen, in other words, might not be a sign of life. It might be the signature of an extinction. And yet, we haven't stopped looking. NASA's Perseverance rover is right now drilling into Jezero Crater on Mars, an ancient lake bed, not looking for living organisms, looking for microfossils, traces of biology that might have existed when Mars still had liquid water 3.5 billion years ago. Even if Perseverance finds evidence of ancient microbial life, it raises a chilling question. Life appeared and then died. That might be the rule, not the exception. Europa, Jupiter's ice-covered moon, has a liquid saltwater ocean beneath its frozen surface, kept warm by tidal forces from Jupiter's crushing gravity. NASA's Europa Clipper mission, launched in October 2024, is on its way there right now, set to arrive in 2030. If anything survives in that ocean, it rewrites everything. But that ocean is sealed under miles of ice, with no sunlight, And the radiation above its surface is among the most lethal in the solar system. The TRAPPIST-1 system, 39 light-years from Earth, has 7 Earth-sized planets, 3 of them in the habitable zone. The James Webb Space Telescope has already analyzed their atmospheres. So far, no biosignatures, no oxygen-methane combination that biology produces, just silence. And that silence is the most important data point we have. The Fermi Paradox asks it bluntly. If intelligent life is common, where is everyone? The universe is 13.8 billion years old. Civilizations could have spread across entire galaxies long before Earth formed. The fact that we see nothing, no signals, no megastructures, no transmissions in 65 years of systematic listening, suggests one of 2 terrifying conclusions. Either intelligent life is so rare it may only exist once in the observable universe, or something stops civilizations before they can spread. Scientists call the second option the Great Filter. Nobody likes discussing which side of that filter we might be on. What we know, built from billions of dollars of exploration, and the most rigorous science humanity has ever produced, is this: Earth is not the default. Life here is not what happens when conditions are reasonable. It's what happens when an almost inconceivable sequence of accidents, a giant impact, a liquid iron core, the exact right chemistry, a freak mutation that turned poison into breath, a gas giant in the outer solar system deflecting comets away from us, all fall into place at once, across 4.5 billion years, without a single link in the chain breaking. Every sunset you see, every breath of that oxygen-rich air, every ocean and forest and living thing on this planet exists because the universe gambles with dice made of supernovas. And for the last 4 billion years, the only planet that rolled a 6 was the one we're standing on. We've searched 4 billion miles. We've aimed our best instruments at the sky for decades. And what the universe keeps telling us in the loudest silence imaginable is that this, right here, is the miracle. Maybe it's time we started treating it that way. Thanks for watching. I will see you next time.